Hello, everyone.
Hello, sir. Good afternoon, sir.
Okay, sorry for the multiple interruptions. I had to restart my tablet. It keeps freezing up whenever I open the file I want to share. So last class, we spoke about many things, which includes the simple cubic in 3 dimensions. And we spoke about simple cubic, body-centered cubic, and face-centered cubic. We also spoke about them being packed, this having a, what do I call it, a sphere, the largest sphere that can occupy this particular cube is what we have in this diagram. And this is the largest 2 spheres that can contain this cube. You will notice that we have a blue sphere and a white sphere. The white sphere is cut into 8 parts, and that is the easiest way to make 2 spheres occupy a cube. 2 spheres occupy a cube that will have the largest size, and both of them will be identical. So the blue and the white spheres, they have the same dimension, and they both fit into this particular cube of, let's say, lattice constant A. And we'll move on to the third, the face-centered cubic structure. There are 4 spheres, 3 blue ones and 1 white one. The 3 blue ones are cut in halves, while the 4th, the white one, is cut in 8. So we have 4 spheres, 4 identical spheres, which is the largest 4 identical spheres you can ever have that will fit into this cube of length A. So from that, I promise that we'll continue from simple crystal structures. So simple crystal structures, the structures that are listed there are some common, let me call it hybrid crystals, in which we cannot really call them completely simple cubic. They are cubic, but we cannot really call them completely simple cubic or body-centered cubic or face-centered cubic. So they are somehow, we can call them hybrid. So we'll be talking about some common ones right away. So the first one we'll be talking about is the sodium chloride structure. The sodium chloride structure is actually face-centered cubic, and it contains 1 sodium atom and 1 chlorine atom per cube, per basis. So let me do something like this. Okay, looking at this structure, forget about these ones that are encapsulated, but look at this structure. When you look at a structure like this, it is obvious that this atom and this atom are not the same. This atom and this atom are not identical. So when we are talking about the lattice parameter or lattice constant here, we'll be talking about from here to here. This is the lattice parameter or the lattice constant. So I want to describe A. We'll start from this particular point and we end at this particular point. So when we circle out the white ones, the white ones here are chlorine. So at the face, let's just consider this face. Looking at this face, you would agree with me that the ones I've circled, if you close your eyes to the green ones and just look at the white, or is it white? Which color is this one? Let's call it ash. Look at the, yes, okay. If you look at the ash ones and you close your eyes to the green balls, what you will see will be face-centered cubic. What you will see will be face-centered cubic if you close your eyes to the green balls and you only look at the ash balls. And when you take it the other way, when you close your eyes to the ash balls and you open your eyes to the green balls, what you will see would also be face-centered cubic. So in this particular case, this particular chlorine atom can be said to be bound with this particular sodium atom. So this chlorine atom and this sodium atom, they form a basis. They form a molecule and they occupy a basis. So they are, the structure shows that it is having its own lattice point here, but this sodium and this chlorine are said to be together. So when we want to label give these coordinates, or we want to give them addresses, since we've said that chlorine is at 000, so we can take this to be our origin 000. But this is origin 000. You know, this is not 1. This is 0 on the x-axis, and this is 1. So when you say 0 to 1, that's 0.1 is also as good as 0. If you remember what we have said about periodic boundary conditions. When we start from 0 and we get to this 0.1, this 0.1 or this length L, this point length L is as good as saying we are at L equal to 0. So, and we can always continue because what we have here is as identical as what we have here. So I hope the noise of the cars passing by is not disturbing. Am I audible enough?
You're audible enough, sir.
Okay, thank you. So from this point, we can call it 000. And this point, we can call it, so on the x-axis, we can call this 0, we can call this 1. And that 1 is as good as 0. So this point, we can label this in 3D, 000. And when we want to label what we have here, this is as good as traveling on the x-axis by half, coming up by half, and staying there at 0. So it's as good we label our axis to be something like this. Say this is, saying this is x, saying this is y, and going in to be z. So when we treat this first one, half, you would agree with me that it coincides with this. And when we treat the second one, half, 0, the half, 0 should be this. And the next one is half, 0, half. Half, 0, half is as good as we starting from the origin, going half on the x-axis, staying 0 on the y-axis, and going half again on the z-axis. So it will bring us here. Please, if you have any problem, interrupt me immediately so that we don't have to waste much time. So this is the origin. We are going to half, 0, half from the origin. This is half on the x-axis, 0 for the y, and half for the z. So at this point, this is the point that coincides with this. So the fourth one is 0, half, half. 0, half, half means that on the x-axis we won't move, it will stay there, and the y half means we'll come up by half, and the z half means we'll come in by half. So you can see this point is the point of interest. Oh boy, let me take that through another route. So when we look at the some atom, the same way we have done dealt, always okay, somebody is sending a message, please. I cannot be reading some other things while trying to explain. So please feel free to unmute yourself to interrupt me and let me know the problem. So for the sodium is said to be at half, half, half. So from the origin here, if we want to go to half, 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 we travel half, and we also travel half. I hope that's clear. From the origin, we travel half on the x-axis, we travel half on the y-axis, we also travel half on the z-axis. So this is the point half, half, half that this particular address is referring to. The next one is half, the next one is 0, 0, half. So from the origin, this is 0. We are not going to the right because it is 0. The other value is also 0. We are not moving up because it is 0. And the third one is half. We are going inside by half because the third value is half. So that means the second address of sodium is pointing to this green ball. So easily we can match them up. And the third for sodium, we have 0, half, 0. From the origin, 0, that means we are not moving to the right. Half, that means we are coming up by half. And 0, that means we are not going inside. Then that means that this is the point that the third coordinates is referring to. So and finally, half, 0, 0. Half, 0, 0 is telling us that from this point we move to the right by half. The next 0 is telling us we won't move up. And the last 0 is telling us we won't go inside. That means this is the bus stop. Then that implies that this half, 0, 0, let me make this a bit neater. It means that this half, 0, 0 is referring to these points. So if you look at what we have, the matching we have done is as good as something like this.
Sir, good afternoon, sir. Excuse me, sir.
I'm with you.
Yes, sir. Please, I would like to ask that, is there any particular ordering in knowing the position, sir? I mean, for instance, if we are given the diagram and we are asked to get the positions in numbers as we have done, sir, is there any way to know which one to come first before the other one, sir?
Are you trying to ask if I can take the ash atoms to be sodium?
No, sir. I'm actually asking that in a case where we are asked to convert a particular diagram to positions as in 0, 0, 0, how do we know which of the atoms to refer to first before the other one?
90. This is we are dealing with periodic crystals, so you can always choose a convenient one. We are dealing with periodic crystals, so I chose the first one here to be the origin 000 because it is convenient. So there is no particular order that says this is the first one you must take or this is the second one. Yeah.
Okay, sir. Thank you, sir.
Okay. So I've tried the eight pen. You can say this is the origin. This is half. This is the origin. This is half 0. This is half 0, half 0, half. And the last one. So what we have done in this big cell is as good as I've just tried to bring out what we did here. So easily you can see that within this particular small building block that makes up everything we have here, we can see that from this block we have, let me clear this some reason. From this building block, we can say we have half Na and half Cl. When you look at this particular cell, you'll notice that we have 4 sodium atoms, and the 4 sodium atoms are contributing one. Each of the 4 sodium atoms are contributing 1/8 of their value to this building block. So this building block. So and that comes out to be half sodium, and we also have 4 chlorine atoms, which are contributing 1/8. Each of them contributing 1/8 of their value, giving us half chlorine. So since we have half sodium and half chlorine, we can say we have half molecule. And so we have half molecule of sodium, though there is nothing saying half molecule of sodium is unreasonable, because when we say a molecule, it should be the smallest structure you can have for that particular chemical compound. So if you look at this our face-centered cubic structure, starting from this 0, ending at this 1, coming up to this 1, 1. So if you look at it, you'll notice that we have 8. We have 8 of these building blocks that makes up something reasonable. If we have 8 of this, we should have a structure that looks like, can I have color blue? You should have a structure that looks like this. Okay, let me explain it like this. Let's take this as a cube. If I decide to cut this cube into two, we should have something like this. Then I can erase this off. Oh boy, it's not cooperating, sorry. Okay, let me draw it this way. This can be said to be a block. This can be said to be another block, block 2. At the back, we can also have 2 other blocks. So here we have block 1, block 2, block 3, block 4. And we can also extend this either upwards or downwards. I think it's better I come downwards. So that is block 5. This is block 6. This is block 7. This is 4. This is 5. Sorry, this is 5. This is 6. This is 7. And we have 8 hidden at the inner corner underneath 3. We have 8 underneath 3. So it means that we have 8 of this structure in this particular place. That means we have 8 times half NaCl, meaning that we have 4 sodium chloride molecules within that face-centered cubic cell. So what I need you to understand is this numbering. I need you to understand the ability of marrying this numbering with points within the cell. So whenever you see 000, it's as good as 111. So because there is no point having 1, because when you get to 1, it's as good as you are at 0. When you get to, and we are talking about half 0, it's as good as saying 1.5 half 0, because when you are at half or you are at 1.5, you are at the same point. As long as 0 to 1 is taken to be the lattice constant. So this type of structure is exhibited by some other atoms, some other molecules, like lithium hydride, magnesium oxide, manganese oxide, lead sulfide, and on and on. So in the case of, let's say, potassium bromide, for instance, where we have sodium, it will be potassium, and where we have chlorine, it will be bromine. So, but the name is sodium chloride structure because sodium chloride is the most popular of them all. So from there, let's go on to the cesium chloride structure. Okay, from the footnotes here, it tells us that sodium chloride is also called rock salt structure. Sodium chloride structure is also called rock salt structure. And going to cesium chloride structure, let's look at the structure before even saying anything about it. Okay, this is the cesium chloride structure. Looking at this, what does it resemble? Which type of cubic crystal does this? Thank you. It resembles body-centered cubic. But if you also try to recall what we mean by body-centered cubic, in body-centered cubic, what we have at the corners of that cube must be the same as what we have at the body center. But right now, what we have at the body center is different from what we have at the corners. So we cannot really call it a body-centered cubic. So in this type of structure, the cesium chloride structure, we can, there is no wrong way. We can take the ash ones to be our cesium and the red one to be our chlorine. We can also take the ash ones to be our chlorine, while the red one to be the cesium. When you try to calculate how many ash balls do we have in this cube, easily we can say we have 8 times 1 over 8, meaning that we have 1 ash ball in that cube. How many red balls do we have? We have 1 times 1, which is 1. So that means that in this cube, we have a cesium atom and a chlorine atom, or a cesium ion and a chloride ion. So we can, so the major point is that in this structure, we have 1 CS and 1 CL. And that means we have 1 CSCl. So what it means is that in the structure, we have 1 molecule of cesium chloride. In the structure, it can be best described as a simple cubic. The structure can be best described as a simple cubic because this particular atom is said to be connected to this particular atom to form a bond. So this particular cesium and this particular chlorine can be said to be to form a bond, to form a molecule. So the cesium, when we take the ash one to be our cesium, then we can say that the position of our cesium is at 0, 0, 0, because at this point we have 0, 0, 0, and at this point we have 1, 1, 0, 0. So, okay, I think for those that haven't gotten so far, we can call this point our 0, 0, 0. This is 1, 0, 0, because we have traveled to the x-axis by 1, and we have traveled to the x-axis by 1, and we have not moved up, and we have neither moved in. So the same thing applies when we move up at this point. This point can be said to be 0, 1, 0. This can be 1, 1, 0. This can be 1, 0, 1. Sorry, that's wrong. This is 1, because we've come to 1, 1, 0. And up here is 1, 1, 1. And inside here we have 0, 1, 1. I'm listening.
So we have 2 110s. I think the one you just labeled 110 is supposed to be 101.
Okay, this is 1, 1, 0. This should be 1, 1, 0, and this should be 1, 0, 1. Thank you. This is 1, 0, 1. Eraser, come out. Eraser. This is 101, right? 1.
Yes, sir.
0, 1. Thank you. So, and the last one there should be 0, 1, 0. So, but like I've said,
Size 001.
no, the last one here, okay, let's look at it together. The last one here, from this point, I'm at x-axis. I did not move inside. So I've not moved to the right. So the first index should be 0. And I did not go in, sorry, I did not move to the right. The first one is 0. I did not move up. So it should be another 0. Thank you. I did not move up, another 0. And I moved in. It should be 1. I think we are cool now. I did not move to the right. On coming in, I did not move to the right, that's 0. I did not move up, that's 0, but I moved in, that's 1. That's 0, 0, 1. Okay. So if you look at this 4, the only difference between what you have in this 4 and what you have in the inner 4 is the third index. So like I've said before, that all the ones can also be replaced with zeros. So every point in this cube can be called 0, 0, 0. And you won't be committing any crime by calling each of the points, or you'll be committing a crime by calling each of the points 0, 0, 0, because 0 and 1 are the same from the periodic boundary condition. So we were doing something earlier. So the address of cesium here can be said to be 0, 0, 0, while the address of chlorine can easily be described as half, half, half. So the cesium chloride structure is a simple cubic, not body-centered. It's a simple cubic. If you have any question, please unmute yourself and speak up.
Yes, sir. Good afternoon, sir.
Okay.
Sir, could I have a question, sir?
I'm listening.
Like the case of this calcium chloride, whereby calcium is 1 atom and chlorine is 2 atoms, no, 1 atom, sir. Unlike in a case like
please,
chloride,
you are too fast. I can't get you.
sorry, sir.
Start all
Sir,
over
you know,
again
like
and speak slowly.
Sorry, sir. Sir, the chlorine has 1 atom here in this calcium chloride. In a case like calcium chloride, whereby the chlorine atom is 2, like how would the structure look like, sir?
The chlorine here has 1 atom.
Yes, sir.
And where did you say there were 2?
Like in a case whereby we have calcium chloride, CaCl2, whereby
Okay.
the chlorine atom will be 2. So like I want to ask, sir, how would the structure look like?
Okay. You see, if you want to know how the structure will look like, then you'll be solving the Schrodinger equation. These ones are known. That is why we have them. So there is we have a database where you can check how it will look like, and you can also decide to do some calculation like the one I was trying to do using quantum espresso in the last class. When I'm not sure of a structure, and I begin to say, okay, let's sodium be here, let's chlorine be here, and I check it, and I see and I check the what do you call it, the total energy. I calculate the total energy of the structure, and I also say maybe it is not even body centered. It shouldn't have a body centered shape. Maybe it is tetragonal, and I begin to do different calculations. So different structures can be tested with the any compound you are trying to check. You can try them with different structures, and the structure with the least energy can be said to be most stable. And that is where you now say that will be the structure of that particular atom. So what's the examples I'll be talking about, they are just limited. I cannot talk about all the examples. In fact, we have about 224 space groups when you're talking about distribution of atoms or different types of crystal structures you can have. So there are different types. So, how can I even, so it depends on the, another alternative is experimental data. When you have done some experiments like X-ray diffraction, those that can also give information about the nature of the structure of the compound you want to investigate. So, but for now, we are just limiting ourselves to some common ones. So, but if you want to explore different types of crystal structures, we have a website that is called Materials Projects. You go to Materials Projects. I think it's .org. So you can go there and you see different compounds have been added to the database. And when you see some compounds, you see that some even exist in different structures. So when we're talking about them being in different structures, under certain conditions, the structure that gives the lowest total energy is said to be likely the one that will be most stable of them all. So, let me clear the screen, and if we add, if this particular structure, it doesn't end there. It can be continue. It doesn't have end.
Hello, sir.
I'm listening.
Yes, sir, you were saying this structure is not a body centered cubic. You were saying
Yes.
it's a simple cubic lattice.
Yes. I said so.
How, sir?
How? In sense that because the content of the body center is not the same as the content of the edges. That's the how. So when we call this to be a lattice, to be cesium, another cesium, we can also put another cesium here, and also put another cesium. This cesium, this cesium. We can also put cesium, so it can continue till we are tired. And if we also come inward, we can always put, I think, so. We can also have cesium. So that means that at the center here of this cell, at the center of this cell, we should be able to also have another chlorine. The chlorine will be connected just like its neighbor, like this. Currently, we don't have a power supply. I would have visualized some of these things on the computer so that you see. I should have done something like this so that we let this go to the right and the left. So just like I said earlier, that this particular chlorine is meant for this. It's meant for this cesium. The same way this chlorine can be said to be meant for this cesium. So each of these other ones, like this particular cesium, it's chlorine will be somewhere here, be connected. So the others up there. So we can also, it's also bound to this. So will be single. They will all have a match. All the chlorines you see here, sorry, will always have a match for cesium. So the number of cesium, if you go infinitely to the left, to the right, the number of cesium will be cesium atoms will be equal to the number of chlorine atoms. So, and that is how to actually say that you have a balanced structure. So don't be afraid that I called it simple cubic, and calling it simple cubic, we only have a chlorine atom within it. No, we have chlorine atom, a chlorine atom within 1/8 of it. So within 1/8, so we have, so this chlorine atom can be said to be surrounded by the effective number of atoms surrounding it is 1. Since these 8 are only, since this chlorine is only seeing 1/8 of each of this, then we can say that this chlorine is experiencing the presence of 1 cesium. And to picture it easily, we can take this chlorine, attach it to this cesium, and say this is 1 molecule of cesium chloride, and take this neighboring cesium, match it with this chlorine, take this cesium, match it with this chlorine, take this cesium, match it with another chlorine that will be at the back somewhere here. You can never, so you can always, of them will go single chloride structure. We can decide to make the ash atoms to be chlorine, while the red ones to be cesium, and you still have your crystal structure. And when I'm talking about 000, taking this to be 000, I can decide to make this my 000. When I take this my 000, I take this my my 100. Can see from this point to this point is like as good as a lattice constant, like from here to here. So when you look at this closely, you'll be saying that this will be forming the center, the body center. When you look at this to be, okay, let me quickly draw a fourth one here. Pen, come here. So when you look at this 4, 1, 2, 3, 4, they are as equivalent as you have been 1, 2, 3, 4. So there is no strict rule around the crystal structures. There is no strict rule at all that governs how you select your origin or how you proceed. Just the major thing is when you consider a cell and you consider it correctly, then you can say that you have considered all the cells that exist within the structure that exists infinitely to the right, left, up, down, center, all around. So the contents of the corners, it would, if this particular atom changes to ash, then we can call it body center cubic. Okay. I thought somebody was speaking.
Hello, sir.
Okay.
Good afternoon, sir.
I'm listening. Good afternoon.
All right. My question is a diagram enough to determine the structure of a crystal? Because the diagram you give us under body cubic, body center cubic, is similar to the diagram you are giving us now. Is it enough to determine the crystal structure?
Okay, I think the confusion will be coming from, are you referring to this diagram?
Yes, sir.
Okay, the diagram here was made to help you visualize easily. To say that we have another one at the center. Every ball here should have the same color. On this page, every ball here should have the same color. That is an ideal way to describe a body centered, to describe a body centered cubic or a face centered cubic. Let me see if I have something to show. I don't know if you can see this.
Yes, sir.
Okay, and you can also see this.
Yes, sir.
Looking at, let me see if I can make it. Okay. Looking at these two now, it is easy to say that this particular one is as good as what we have in the middle one. Yeah, let me come out here. It's as good as what we have at the middle one. A ball has been cut into 8 and made to fit into a cube. And the same ball can also be made to stand into the same cube without we cutting it at all. So, and coming to the body-centered cubic, this is something similar. These are two identical balls. Two identical balls. I'm sure you know this ball is familiar. I use it to play table tennis. This ball is used for table tennis. So we have two identical ones that are made to fit into this particular cube, though it's now a bigger cube, and it looks like a body center cube. So what we have inside is as good as what we have outside. The size of what is four. Hello, can you hear me?
Yes, sir, I can hear you.
Okay, sorry. I'm connected with my phone and somebody called me. Okay, so, and this is just like what you have in the face center cubic. So in this cube, we have 4 identical tennis balls that were cut to fit into this shape. One was cut into 8, the 3 others were cut into halves. So this is a project of one of my former students from education. So we should thank the educators for making this particular, I call it toy, to show us exactly, this project was to describe parking fractions in cubes, in cubic structures. So what is his name? Is it Jalili Shitsu Jalili? So the difference in colors we have here are just to make you visualize things easily. So you can replace all of them with color white or color green as you like it. So do we have any other? So silence misconsent. Hexagonal close pack structure that has a packing fraction of 0.74, which is the same as what we have in face-centered cubic. And spheres are arranged in layers. So if you have a lot of identical balls, you can arrange them. There is a way you arrange balls on the table such that you will know that you have maximized all the spaces on that table. And when I'm talking about you arranging balls on the table, I'm talking about something like this. If you want to arrange the balls on the table and you have done something like this, the fact remains that you have not, that is not hexagonal close back. In hexagonal close back, you can see that the spaces you could have had here has been occupied by some other atoms. So they can be arranged in different styles, like I've written in the text. You can just read through them. You can decide to what we have this layer is typed on is to look at layer B. Layer B is saying that we'll place a sphere. So we can have a second layer by placing another set of spheres. So the center of the spheres of layer A are the black dots we have here. The center of the spheres are the black dots we have here. So we can also say we want to have a layer B such that the center of the spheres of those will now be at this point. So we'll be talking about we having some circles, things like this, and say our layer B should be something like this. So wherever we have layer B, we have something like this. Layer B. This is not properly drawn anyway. Let me try again. I wish I can have a circle. I wish I can copy this circle and reproduce it all around. So don't let us waste time with this one. Let me just draw the crude one, which is we have a circle, pom, 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 pom. I think this is better. So wherever we have layer B, we have put another ball in there. So, and our layer C will be the third layer, such that the center of the balls will now be in places like this, such that, so by doing that, you'll be having this close, this, the initial diagram we had there was talking about we having these balls closely packed on a single layer. So by the time you do that for, you arrange balls on layer B and layer C, when you look at it from the side, from different angles, this is what you will see. This is what we are seeing from the top. When you look at it, when you arrange it, this first in this manner, and you look at it from the side, you also see this. When you look at it from the left and the right, you also see things that look like this. So if you want to play with the mathematics, the coordination number is 12, and also the ratio of the height to the lattice constant. So lattice constant here will be from this point here to this point here. The length here is lattice constant A1, and having constructed this, will be having, it will have a height. When you make 3 layers, it will have a height, and the height will, the ratio of the height, that is C over A, the ratio of the height, A3 over modulus of A3 over modulus of A1 will give you 1.633, which is obtained from root 8 over 3. So if you want to play a game, you can do that as a game to obtain this 1.633. So now let's move on to diamond structure. So diamond structure is face-centered cubic. In sodium chloride, we call sodium chloride face-centered cubic, and the same thing is happening now. We are also calling diamond structure face-centered cubic. But what is unique about diamond structure is that there are 2 face-centered cubes that are interlaced, that are interconnected. 2 face-centered cubes are interconnected to such that the origin of the first one is, when taken as 0, 0, 0, the origin of the second face-centered cube is located at 1/4, 1/4, 1/4. So you have to imagine a face-centered cube. Now that face-centered cube, imagine another face-centered cube within it. So when you can imagine another face-centered cube within it, such that the origin of the second one coincides with 1/4, 1/4, 1/4 points of the first one, then what you have is diamond structure. So the diamond structure has two lattice points. I think I would modify this. It has 2 lattice points per primitive cell, and this sentence I did not read it very. And the materials of this category exhibit tetrahedral bonding structure. So let's look at how does a diamond structure looks like. Oh, I don't have it here. So, okay, let's put that on one side. Let's talk about the zinc sulfide structure. The zinc sulfide structure just looks like the diamond structure. The difference between the zinc, so the diagram we have here is as good as the diamond structure. If we can just imagine that, diamond is element carbon. Diamond is carbon. So if you imagine this particular structure, when you imagine that it is all carbon, when all these balls are having the same color, then you can say you have diamond structure. When all these are having the same color, when they are having, all the lattice points are having the same elements, then we can say that we have diamond structure. So that is just a basic difference between diamond structure and zinc sulfide structure, is that in zinc sulfide structure, we have 4 zinc atoms and 4 sulfur atoms that makes up the conventional cell. So let's look at, so when we look at these addresses we have here, look at these addresses, 0, 0, 0 as zinc, that means this is our zinc. 0, half, half, 0, this is half, 0, this is second one, and the third one is saying half, 0, half, 0, After that is referring to this. So these are the four, in order not to waste our time. This 2, 3, and 4 are the 4 zinc atoms described in that in the addresses. The others are not really relevant. The others will be described by the neighboring cells. But for this particular cell, we can take these 4 to be the major point of reference. While the sulfur atoms, the 4 sulfur atoms, when you want to go through the 4 sulfur atoms, the first one is saying 1/4, 1/4, 1/4. So we, from the x-axis 1/4, the y-axis 1/4, then you go in 1/4 to meet this. The second one is saying 3/4, 3/4, 1/4. You travel here 3/4, travel up 3/4, and you go in 1/4. The third one is saying 3/4, 1/4, 3/4. So you travel to the right by 3/4, you go up by 1/4, and you go in by 3/4. You can see that the color of this purple sulfur is made to be somehow faint because it is inside, unlike these ones that are like these ones that are bright. These ones are bright, but these two are fade because they are inside, far inside compared to the ones outside there. So finally, 1/4, 3/4, 1/4, 3/4, 3/4. So that is, so I'm referring to this point, 1/4, 3/4, 3/4. That is as good as we coming from here, from the origin, we move 1/4, and we move up 3/4, and we also travel in 3/4 to get to this point. So if we decide to make the yellow balls to be if we decide to make the yellow balls to be sulfur and the purple balls to be zinc, we'll still have zinc sulfide structure. When we decide to take this particular, decide to take this particular atom to be our origin, we'll still achieve the same results. Because when you decide to look at this to be your origin, then it's as good as this being half, 0, half. Sorry, half, 0. And this, when you take this to be your 0, 0, 0, then this point is as good as we coming to the right by half, and we go up by half, and we stay there 0. So that means we'll be staying here at 0. Well, we'll try to connect to the third one from this point. It's like we move up by half, so that this we do not move to the right. We move up by half, and we go inside by half again. We'll get here. And the same thing applies here. When we travel to the right by half, we will get here. When we don't move up, that is 0. And when we go inside, we'll still meet this fourth one. So another thing we can also play with in this structure is to say that how many zinc atoms do we have in this cell? It's obviously, how many zinc atoms do we have? We have 8 at the corners. 8 at the corners times 1/8. That's equal to 1. We have 6 at the faces times 1/2. That is 3. That means we have 4 zinc atoms. How many sulfur do we have? The 4 we have here are all within. The 4 we have here are all within the cube. So that is as good as saying 4 times 1 equal to 4. So in this cell, we obviously have 4 zinc atoms and 4 sulfur atoms to give us 4 zinc sulfide molecules. Also, we can also, like I said earlier, this, or like I've said many times, these are just conventional cells, but they can grow infinitely in space. It can grow infinitely in space. So we can decide to, so like this is the left-hand side, this particular point is the left face of this cube. Somewhere else, it is the right face, is this right center of another cube. It is the left center of this cube, but it's the right center of another cube. This cube is the right center of this particular cube, but it's the left center of another cube that we are about to draw. So it has no limitation. So we can also have another zinc here, another zinc, another zinc, another zinc. At the faces, we have zinc. So everything continues without any end in sight. Is there any other thing I should tell you? So, okay, when we take this to be our origin, like we attempted earlier, and we say this is the center of the face, then you should be expecting another one at 1/4 here, which this will be, which when you look at this, there will be another one here. And when we come up, we'll find another point. I should have used another color for this one. So at up here, we still have another point at 1/4 up here. And when we also consider what we have here, we also have another point here at 1/4 for this cell. So you can see that this alone forms the face of a face-centered cubic, just like we are used to. So I hope we would have a power supply in next class. I would visualize growing this unit cell all around so that we'll see how they really look like. Do we have sorry, we started very late due to technical issues. Let me try to run through this index of planes so that when we meet next week, we'll just start reciprocal lattice. So still on direct lattice, there is just like I've shown you how to give points addresses, 0, 0, 0, 5, planes also have addresses. Well, and how do we describe a plane? A plane is a plane.
Is
that the question?
I know now. Someone sent an email. Email.
Okay. If we want to describe a point, the best way to describe a point is to talk about its coordinates in space. When we want to describe a line, the best way to describe a line is to talk about 2 points in space. So when we have 2 points in space, we can 2 points in space is sufficient to describe a line. And when you wait to describe a plane, at least you must have, so any 3 points in space will always be able to go through. Imagine that. So a sheet of paper is an example of a plane, and it can go through any 3 points you choose. And those 3 points must be non-collinear. That is, the 3 points should not fall on the same line. So, so in a crystal, or in a crystal structure, the planes also have addresses. And the way we address the planes is the index system for crystal planes. So the way we address the planes is the index system that we'll be talking about it. So, and it has to, and what I've written here is just talking about the rules. How do we determine the addresses of these planes? So the first thing to do is that we find, number one, find the intercept on the axis in terms of the lattice constants, A1, A2, A3. And note that an intercept of infinity is 0. So when, so that I have an example here, which is saying that A1, A2, A3, you're saying that A1, A2, A3 are 4, 1, 2, respectively. So if A1, A2, and A3 are 4, 1, 2, respectively, what is the, so now we are talking about a point 4 on axis A1, point 1 on axis A2, and point 2 on axis A3. We are imagining a sheet of paper cutting in through points 1, 4, and 2 on A1, A2, A3. What is the address of that plane? So we find the intercepts on the axis, 1/1. The second thing we do is, we found the reciprocal, we've done the second thing, which is, then we link to 3 integers that will have the same ratio as 1/4, 1/1, and 1/2. Which mathematics are we going to use to get those 4 integers? What do we do next? Can somebody tell me?
Find the LCM.
What's your name? You deserve a bonus mark for that.
Michael. I don't need you, Michael.
Okay. So, so 4, 1, and 2. We find the LCM of 4, 1, and 2. That should be 4. So here we have 2. So the LCM is 4 anyway. So we use 4 to multiply 1/4. We get 1. We use 4 to multiply 1/1. We get 4. And we use 4 to multiply 1/2. We have 2. So 1, 4, 2 in parentheses is the address of that plane. So 1, 4, 2 is the address of the plane that cuts that cuts 4, 1, 2. So the plane that cuts 4, 1, 2 is 1, 4, 2 in parentheses. And when we have cases where the plane cuts through a negative axis, that is where we use bar, just like we have here. So, and some examples, pictorial examples we have here. So these are cubes, and the first one here is telling us that this is cutting A1 at 1. It is cutting A2 at infinity, and it's cutting intercepting A3 at infinity. So the reciprocals will be 1/1, 1/infinity is 0, and 1/infinity is 0. And the smallest three integers that can represent the reciprocals is also 1, 0, 0. So the same thing applies to this point. This when we come to this, for instance, the plane cuts the plane intercepts the A1 axis at 1. It intercepts the A2 axis also at 1, and the A3 axis at infinity. So when you do that, you also have 1, 1, 0. So every face of the cube has an address that used to say this is so every face of the cube can be described as a plane, and they can all be addressed using the Miller indices, using the index system of plane. It's also called Miller indices. So next class we'll be talking about reciprocal lattice. Do you have any question? In the absence of any question, we'll meet next week. Bye-bye.
Bye, sir.
Okay.